Welcome friends, Igor is here, and in this video we will learn how to solve any linear system efficiently by using the Gauss-Jordan elimination algorithm. In this lesson we will describe the Gauss-Jordan elimination algorithm, apply this algorithm to solve several systems of linear equations, and finally discuss the uniqueness of the reduced row echelon form of a matrix. Let's get started. Let's quickly recap what progress we made towards our goal of solving linear systems. We found an efficient way to represent linear systems by using augmented matrices. We proved that performing row operations on the augmented matrices preserves the solution sets of the corresponding linear systems. Also, our finish line goal is to reduce a given augmented matrix to the reduced row echelon form, because the reduced row echelon form represents a linear system that is easy to solve. All that remains for us to figure out is how to transform any given matrix into the reduced row echelon form matrix. There is a simple algorithm that allows us to do this. This algorithm is called the Gauss-Jordan elimination. Step number 1 is to locate the leftmost non-zero column. The second step is to swap the top row with another row if necessary to bring a non-zero entry to the top of this column. Step 3 is to scale the top row to produce a leading one in place of a non-zero entry. Step 4 is to use as many replacement operations as necessary to produce zeros in the column below the leading one. Step 5 is forget about the top row, imagine it is not present in the matrix, and start again from step 1. Keep going through steps 1 through 5 until you exhaust all non-zero rows. In steps 1 through 5, you go from the top row of the matrix to the bottom of the matrix. But in step 6, you're going to reverse the direction and go from the bottom of the matrix to the top of the matrix. You will use as many replacement operations as necessary to produce zeros above each of the leading ones. By completing all these steps, you will arrive to a matrix in reduced row echelon form. Now we have an efficient way to solve any linear system. We start with a given linear system. Then we represent this system by its augmented matrix. Then we use the Gauss-Jordan elimination to transform the augmented matrix of the system into the reduced row echelon form. Finally, we solve the linear system whose augmented matrix is the reduced matrix from last step. This solution set of the transformed linear system is the same as the solution set of the original linear system, because in every single step we used row operations which preserve solution sets. This procedure provides a final realization for our strategy of solving linear systems. We start with a difficult linear system. We represent the linear system by its augmented matrix. We transform the augmented matrix to a simple form. Then we solve the easy linear system which corresponds to the transformed reduced matrix, and what we get is the solution set of the original linear system. Now let me illustrate this procedure. In the first example, we are going to solve a linear system in 3 equations and 3 variables. We start by representing this linear system by its augmented matrix. Now our goal is to apply a sequence of row operations to transform this augmented matrix into a matrix in reduced row echelon form. Let's follow the Gauss-Jordan elimination algorithm. Step 1 is to locate the leftmost non-zero column. In this case, it is column number 1. In step number 2, we have to ensure that we have a non-zero entry at the top of this column. In this case, we already have a non-zero entry at the top of this column, but let's look one step ahead. We know that the next step that is coming is to scale the top row to produce a leading one. But if we have to scale by -1/7, then we'll introduce some fractions that will make our computations more difficult in the future. Why not instead swap rows 1 and 3 and avoid having to scale to obtain a leading one? Now that we have a 1 in the proper position, we will use replacement operations to produce zeros below this one. In the second row, we have 5, and therefore we are going to multiply row 1 by -5 and add the result to row number 2. In row 3, we have -7, and therefore we are going to multiply row number 1 by 7 and add this to row number 3. This completes step 4. We produced zeros below the leading one. Also note that there are no zeros above this leading one, and that means we already have a ready pivot column. When a pivot column is complete, I will put the leading one in square to indicate that we are done with this particular column. Next, step number 5 says forget about the top row. So now we are going to pretend that row 1 is not present in the matrix. We need to go back to step 1 of the algorithm now and locate the leftmost non-zero column. In this case, it is column number 2. Next, we need to ensure that we have a non-zero entry at the top of this column and then scale it if necessary to make it into a leading one. Now we see that no matter which row we scale, we are going to introduce fractions into the matrix, and therefore we are not going to swap the rows, we are simply going to scale row number 2 by 1/5. Now we have a leading one in row number 2. And we need to use replacement operations to produce zeros below this leading one. There is only one entry below the leading one. It is equal to -6, and therefore we are going to multiply row 2 by 6 and add the result to row number 3. This completes our second run of the algorithm from top to bottom. Now we are going to forget about row 2 and go back to step 1 of the algorithm. We need to locate the leftmost non-zero column, and in this case it is column number 3. Next, we scale this row to produce a leading one. Then we would have to use replacement operations to produce zeros below this leading one, but there are no rows below this one, and that means we have completed steps 1 through 5. We have completed our sweep from the top of the matrix to the bottom of the matrix. Now we are going to start at the bottom of the matrix and work our way up to clear all the entries above the leading ones. We start with the bottom row, it is row number 3, and we take the leading one in this row and we use replacement operations to produce zeros above this leading one. First, we scale row number 3 by 13/5 and add the result to row 2 to produce a 0 in row 2 above the leading one. And then we scale row 3 by -4 and add this to row 1 to produce 0 in row 1 as well. Now we have a matrix in the reduced row echelon form. We have completed the algorithm. Let me now demonstrate why a linear system whose augmented matrix is in reduced row echelon form is easy to solve. This matrix represents the following linear system, and the solution is obvious. This is a unique solution to the transformed linear system, yet we know that the original linear system has the same solution set, and therefore the original linear system has this unique solution. Let's solve another linear system. First, we represent the linear system by its augmented matrix. And now we are going to apply the Gauss-Jordan elimination algorithm to the augmented matrix. First, we are going to locate the leftmost non-zero column, and it is column 1. We already have a leading one at the top of this column, so we need to use replacement operations to produce zeros below the leading one. First, we need to eliminate 2 in the second row, so we need to multiply row 1 by -2 and add to the second row. Then, to take care of 1 in the third row, we multiply row 1 by -1 and add this to the third row. Next, we are going to forget about the top row and start again with step 1. Locate the leftmost non-zero column. In this case, it is column number 2. Then, we already have a non-zero entry at the top of this column, and we need to scale row 2 to produce a leading one. Therefore, we need to multiply row number 2 by 1/3. Next, we are going to use this leading one to produce 0 below. For this, we multiply row number 2 by -2 and add this to row number 3. Next, we forget about this second row and go back to step number 1. But now we only have row number 3 left, and it is a 0 row. We cannot locate a non-zero column, and therefore we completed our sweep from top to bottom. Now we need to work our way from the bottom to the top to clear all the entries above the leading ones. We start at the lowest leading one, which is located in row number 2, and we need to make the entry above this to be equal to 0. That means we multiply row 2 by -1 and add this row to row number 1. Now, this matrix is in reduced row echelon form. Let's solve the linear system which is represented by this matrix. First, let's observe that the last row, the 0 row, corresponds to the equation 0 equals 0, which is always true no matter what the value of variables, and therefore this equation imposes no restrictions whatsoever on the solution set of the linear system. We need to concentrate on the other equations which correspond to non-zero rows. Let's write the linear equations which correspond to rows 1 and 2. We are going to solve each equation for the variable that corresponds to the leading one in the equation. So we solve equation 1 for the variable x1 and equation 2 for the variable x2. Now you should be able to see that this linear system has infinitely many solutions, because you can assign any value to the variable x3 and compute values of x1 and x2 that will ensure that all equations in the linear system are satisfied. Because we are free to assign any value to the variable x3 and still get a solution to the linear system, we call such a variable a free or independent variable. We are ready to write the solution set to our linear system in a vector form. We have this solution vector, and notice how we represent these infinite solution sets. x3 is a free variable, and so it is free to take any value, but x1 and x2 are defined in terms of x3. This is a parametric description of an infinite set, because to produce any particular solution of this linear system, all you have to do is assign a specific value to x3. Let's work out one more example. In this case, it is a system of 3 equations in 4 variables. Let's write the augmented matrix of this linear system. And after we apply the Gauss-Jordan elimination algorithm, this is the reduced row echelon form that we obtain. But let's look at the last row of this augmented matrix. It corresponds to the equation 0 equals 1. And this equation is always false. It does not have any solutions. No matter which values you assign to variables, they will never satisfy this equation. Because we have one equation in a linear system which has no solutions, it means that the entire linear system has no solutions, and in this case, its solution set is the empty set. Finally, I wanted to remark that the reduced row echelon form of any given matrix is unique. You might have noticed in my step-by-step explanation of the algorithm in 2 examples that you have some freedom of choice and you can take different directions how you reduce the matrix to the reduced row echelon form. The natural question is this: if you use different approaches, will you get different reduced row echelon forms? The answer is no. No matter how you reduce the matrix, you will always end up with the same reduced row echelon form. Therefore, you don't have to worry if you apply some ad hoc approach to optimize the algorithm for a particular linear system. You will still end up with the correct answer. One bonus application of this uniqueness result is that it allows us to decide whether any 2 given matrices are row equivalent. What you do is you reduce each matrix to the reduced row echelon form, and then the matrices are row equivalent if and only if they have the same reduced row echelon form. If you found this video useful, please like and subscribe to help others discover this content. In the next video in this series, we will discover a systematic procedure for describing infinite solution sets. I will see you later.